I am very honored and pleased once again to present Pablo. Pablo Santos will talk to us about the Picard-Vessiot theory and Liuville's theorem, where algebraic geometry meets differential equations. So please, Pablo.
So first of all, I want to discuss the motivation behind this. For me, as a mathematician or as a student, I feel like we're all here for a reason because we feel some motivation behind our research or study or finding some purpose within maths or science or whatever it is. And for me, this was really presented when I first encountered the Galois theory and the group theory and symmetries, because I found some motivation behind finding some purpose or reasoning behind the structures that might explain why something is solvable or why something is not solvable. And well, I've encountered that we have things like differential equations, which are very useful for understanding the behavior of the real world we have, and we might want to be able to see to what extent we can interpret this. And so this talk is more about this rather than me trying to come to a crowd and saying, I will prove this to you and I will show you this, because at the end, I am not a professional at this. I am a student just like all of you, and you want to learn, and I want to learn, and I'm here to learn with you. So today I will be learning about, talking about Picard-Vessiot theory, which is just my way of, or Piccard and Vessiot's way of studying the solvability of linear differential equations. And we're going to be utilizing algebraic methods, which I will go over later. And specifically, this is like an analogy that comes from what Galois did initially with polynomial equations, where he studied the way that polynomial equations are able to be solved using operations from the coefficients of this polynomial. And by the way he studies them is, instead of trying to compute manually or trying to algebraically demonstrate that like a specific number is a solution, well, rather we would like to study the structure of the fields where these coefficients lie and see how we can start extending them finitely until we reach some specific field where we can find the solution. And once we have this scheme of extensions and fields where we can find our solution, then we can study some symmetry of these the solutions of this polynomial to then be able to interpret if this polynomial is solvable. And so my idea today with you is we'll be doing this for differential equations. And this was developed by Piccard and Vessiot. And the idea is we look at this group called the Galois group, which is in the most easy way to think about it is I can think of an object. Perhaps I will like grab my phone and I will like to study like all the different actions I can perform on this phone and see how many of them represent the symmetry of this object, and how these symmetries will hold an underlying structure behind it, which will allow me to interpret how the fields of a polynomial or a differential equation in this case will behave. And so I have said this kind of reasoning comes from Évariste Galois, French mathematician from the 19th century, and he and one of his most important results, which wasn't actually a result he did, he proved that there was a correspondence between the structure of the fields of a polynomial equation and its solutions, and the subgroups of this group of functions, or more formally known as automorphisms with specific properties, and such that when you like can dissect this this group into subgroups and show that it's solvable, then we can also show that our polynomial and its field extension will be solvable. And so we reduce a problem of studying infinite fields and like extensions, which involve infinite number of numbers, into a finite problem, a discrete problem, which involves using permutations of solutions, symmetries, and subgroups of these group. And so the legacy is that after he developed this correspondence, a bijective correspondence between the fields of a polynomial and the subgroups of the Galois group, we were able to see that we can extend our field of coefficients up to a splitting field called, because we can split our polynomial, to the point where we can look at its Galois group and see that it will also deconstruct into normal subgroups with abelian quotient groups, and this will be elaborated on later. And so I will be trying to go over a very important theorem called Louville's theorem, which will be regarding the solvability of a linear differential equation. In a general state, I will be looking at a system of differential equations, which is a representation of an nth order differential equation, which can have coefficients be from any field of or ring of polynomials. And what I mean by this is, normally in class, or like I've studied in my class, that we have differential equations that have coefficients be like real numbers. But these differential equations will also have polynomials as coefficients. And that's why this might be very convenient, or might be useful, because I was interested in how we can use this. And for this, I will be going into the like a light surface of what is known as algebraic geometry. And it's very useful because using algebraic geometry, I can study the structure of this new group called the differential Galois group. And this group is a closed set under a space that we call the Zariski topology, because it is an object called an affine variety. And the idea is, I don't want to bombard with just new definitions, because my point is, I want to show how I can apply this sort of criterion or method to know that a differential equation might be solvable by exponentiation, taking integration, and like creating this closed space where my differential equation is solvable. And so, first of all, we have differential fields, and differential fields are, it's just going to be a field of polynomials or functions or rational functions, which will be treated as coefficients if we go back to the polynomial analogy, I'll say. And then we will study affine varieties, which will be the closed sets of this space that we will be creating. And the affine varieties are just elements of an affine space, such that we can take a number of polynomials, and these and this affine variety will zero the polynomials. That is, when we input these numbers, they will zero the polynomial, and they will give us zero. So they're roots in a sense. And finally, we will look at linear algebraic groups, which are going to be a matrix that are defined by polynomial equations, and they are groups which act on a linear space. And this is particularly important because when we're going to be extending our differential field, we're going to want to create some basis for the linear space of our solutions. Because in the end, we know that differential equations, they form a space. It's not like we just have 5 solutions, right? And this is the main deviation from the original theory that Galois developed, because when you have a Galois group in polynomial equations, well, it's going to be finite. There's a finite number of ways I can rotate this phone, right? There's a finite number of ways I can permute my roots. And one of the examples I like to give about permutation of the roots is the conjugate of a complex number. You know, you can take a quadratic equation with complex roots, and we know that both like the complex number and its conjugates are going to be the roots, and so we can permute them, and this will leave it intact. And we tried to create this idea of conjugacy, but in this differential field, and not necessarily from the complex numbers, but rather we will be grabbing all these polynomials in our field, and we will be extending it by adjoining or combining, or just including into our space the solution space. And so the theorem I will be proving is, or not proving, but like going over and how to use, is a theorem which talks about a Picard-Vessiot extension, which is this differential field extension. And this extension is solvable by quadratures, which means that you can apply integration, exponentiation, and any sort of algebraic function. And we will be able to solve this extension only if, and if and only if, the identity component of its differential Galois group is solvable. And so we will go over what this means. And so as an example, like we might be given some differential equation like this, and I might ask you, like, does anybody know if this is solvable or not? And we can try to, yeah.
I think I know the answer. I'm guessing it's not solvable since you mentioned it. This is my confirmation bias.
Yeah. So so it is unsolvable, and by unsolvable I mean we cannot express it without elementary functions. And so the way we do this is we will apply this criterion, and we will look at the identity component of the Galois group, which is a component I will describe in a second. So the idea is I want to first show the framework and the method that we utilize, because I think that's more relevant for everyone. And then additionally, I will explain what the identity component is and what a Picard-Vessiot extension is. And so here I have a few definitions, and I think that these definitions are very important because I'll start with a fundamental matrix solution. And so any of the systems we have, we can represent it as a linear system, and we can take an nth order differential equation, and we can represent it as a system of n differential equations, all first order. And this is what this represents. And this will be some type of derivation or differential operator such that it will it's linear in addition, so we can separate the addition of functions in which we apply it. And it will also follow the product rule that we all love from calculus. Then we also have a matrix which represents the system itself. And it's very important to understand that, if we go back to our linear algebra class, we know that a matrix, like when we have a linear system, like a homogeneous system, for example, this matrix will have numbers, right? And these numbers will dictate the behavior of the system, not the system, but like literally we take the product and we can see the coefficients of the different variables. So in this case, it's kind of the same. But in this matrix, it's going to have polynomials, right? Because that's the whole point, is that we will have polynomial coefficients, and this will ideally be our solution. And so that's why I get the definition of the fundamental matrix solution, which is just some matrix, which is an element of the linear algebraic group, which I will get to this in a second. And K is going to be our field containing, let's say, ideally the solutions. And the idea is I want to be able to find a matrix that every column is going to be a solution to my differential equation. And this is what it says right here, right? Because I can just input this matrix, and I can take one of the columns and I apply the derivation, and then I multiply the solutions by this matrix, and then boom, I get an equation equality. And so what's very nice about this matrix is that it will form a basis for the solution. And the idea is I'm gonna, like in Galois theory, I will start permuting this basis. And what is really interesting is I will show that the Galois group, when it acts, it basically does a basis transformation of the solution space. And so of course we need the notion of extension. And for a differential field extension, it's just generating the base field with our fundamental matrix solution. And so what happens is we have all these polynomials. I don't know, I'll take like polynomials in C, and we want to combine them with what I would ideally want to think is the...
Give an example.
Of course, I'll give an example. So
Annotate.
So what do you need an example of?
So you were talking about the differential field extension.
So, okay, I'll provide an example. We can have, for example, let's say we have our base field F be equal to all complex polynomials. So this is just going to be any polynomial with coefficients in C. And we might create some field extension to express some solution. And so the easiest example I can provide maybe is going to be the well-known exponential differential equation, right? And as we know, the like exponential equation e to the x we cannot represent as a polynomial in complex solutions, at least not finitely. And so we can create some extension by just literally adjoining e to the x. And by this, I mean is we're going to include e to the x as an element of our field. And then we will be able to create all possible combinations or linear combinations, if you want to think, of e to the x with polynomials. So I will take some polynomial x squared plus 1 and multiply it by e to the x. And I can do all these types of combinations. And this, I think,
it's under this.
Okay, I see. You need to use your hand. Use all fingers.
Yes. Sorry. And so, okay. Of course, for this example, it's obvious. And what I will go to show is how the Galois group generated by this extension is solvable. And so that's why we can solve this differential equation.
So if I understand this correctly, we take some solution and we join it to the original field.
Yes.
And we get a new field.
Now, this might sound like it's pointless because I kind of know the solution, right?
Exactly.
But I will provide an example, like the differential equation example I showed, and how we can do this without the solution.
Also, when you adjoin the new solution to the existing field, how do you know that the resultant space is also a field? Because you're just adjoining a particular element, you don't have the inverse of that.
Well, you can. So okay, yeah. I did do skipped over. So it's not necessarily a field. It can be. It's also called a Piccard. A differential ring. In my definition here, like this should also be. This should be called a ring. And if this is also a field, then it will be called a field. But like in the example I just provided, then it's not a field, it's a ring.
Yeah.
And so, yeah.
So would you say it's a bit deceiving from Picard and Vessiot to call it differential field?
No, it's not deceiving. I just called it a field because in normal, original Galois theory, we don't have this problem of it being a field or a ring. But when you adjoin this new expression or this solution, it might be like transcendental over the original field, and that's why it might not be a field anymore. And so we get to the definition of a differential Galois group, which is going to be all the permutations, or not the permutations, but the functions that permute the matrix, right? So maybe if I do like an example of the matrix, the matrix is just gonna look like something like I don't know, some y1 and y derivative 1, y2, y derivative 2, and so I can create some function of this group G, I'll call it, and I'll get some sigma out of G, and I will apply this G to my set. And the idea is that G will preserve K, and it preserves the linear properties of the system, first of all, and it's defined to be this way. And it also commutes with the derivation. We also assume, since it's an automorphism, that it's going to be bijective, and that for any x and y, we can apply sigma of x star y, and we can separate this. Yeah, and we also assume that whenever we apply it, what means by fixing is that whenever we apply sigma to an element of f, this will just give us f. And furthermore, we can create the field of constants, and this one should be a field, but I'll call it ring just to make sure. And this is just all the elements f of our field, such that if we apply the derivation, this will give us 0. So it's constant. And so we can define this every sigma element of G as some matrix of transformation. I'll call it M sigma. And what it means by it being over C is that the elements of this matrix will be constants, first of all. And second of all, since the matrix will preserve the form of a basis of this will still be a basis. Like, think of each of these columns to be a solution. And so I can have one which is like n-sized, and each of these, I'll call them like x1 and x2, are linearly independent, and they will form a basis to the solution space. So whenever I apply M to Z, this will just give me some other Z prime such that this is also a basis of the, a basis of the space. And finally, I will get to the identity component of the group. So, okay, let's think about it, like, because it starts to like get out of our control, and this is not nice. So we have some group that acts on our basis or on our space of solutions, specifically on the basis, and it transforms the basis, and it will create some structure. And contrary to original Galois theory, this group is not necessarily gonna be finite, because we can apply a continuous, like these operations can be continuous, right? This field of coefficients could be all complex numbers, right? And so we can apply all types of matrices from complex numbers. And when I say a linearly algebraic group, like for example of C, I mean all n times n matrices with coefficients of C, such that it is invertible. And so I get to the identity component because the theorem states something very important about the component. That is, if we can prove that this component is solvable, then our differential system is solvable. And so this G identity component is just going to be some subgroup of G, such that if you take the quotient group of G and G identity component, this will be a finite group. And furthermore, it will be connected in the Zariski topology. And what I mean by this is we form a space, as I said earlier, where every closed set is going to be some affine variety. That is, it's going to be like a set of points which are solutions to polynomials. And furthermore, it's going to act on a linear space. So it's going to be a linear algebraic group, which is an object which is studied in algebraic geometry. And we create a space, a topology, and it's not rigorously defined as a topology, but it is convenient because it is very useful to study the properties we normally study in a topology, like connectedness or being Hausdorff. And for the example of the Zariski topology, it is non-Hausdorff, and this will be useful for us.
So what's next?
So now I will provide an example and utilize this. Because now I've given a lot of
notation.
I've given a lot of like background on what this all means, but it's kind of useless, right? And so maybe we have computer scientists here or like physicists who want to know why this is useful for them. So we have some system and we convert like some nth order differential equation. Now we convert it to a first order system, as I said. Then we will construct a fundamental matrix solution, and we will prove that it's linear independence by computing the Wronskian. By the Wronskian, it's just a fancy way of saying that we're going to find the determinant and show that it's not equal to 0. And the reason it's Wronskian is because the matrix is going to be a matrix of functions with their derivatives. So it's just a formality to say it like that. And then we will determine the Galois group, and we will identify like the symmetries, and then we will check the solvability of G identity component, because then we can show that it's solvable.
Small question: is G not going to be in G?
Yes.
Okay.
Well, actually, for the example I've chosen, it is the case that G is equal to the component, because first of all, G identity component or I'll call it G naught. The G naught is connected by definition to G, and we are in and these are all closed sets in a non-Hausdorff space. And so by being connected and Hausdorff, non-Hausdorff, sorry, this will it's some development to show that they will be equal. Okay. And so now I will provide an example of how to use this. The first example is almost trivial, which I had already told you. And so we take this equation, we construct the fundamental matrix, and then the determinant is just itself, and it's not equal to 0, so it's linearly independent. And so this is a very important step, because this is the most important step. And how do I just assume that this is going to be isomorphic to the multiplicative group of complex numbers? And when I think of this, so how does a space work? A linear space, when we construct it from its basis, we just take all linear combinations, right? And since we have just one element in the basis, then all linear combinations will just look like a e to the x, right? And in our definition, I said that when we construct this, the Galois group, it's going to be over the field of constants. So in our case, I kind of implicitly assume here that we're working on the complex numbers. But then all these transformations are like one-by-one matrices with elements of complex numbers, and we're doing multiplication, so our group is going to be this. And then using, we have a solvable group, and we know a solvable group is solvable if, well, first we have it, we need to show that we can create a sequence of normal subgroups such that we can dissect the group until we reach the original group, and this being equal to the identity element. But we don't really have to do much, because for something to be normal, we have to apply like a conjugate, I don't know, G and G inverse. And since our group is abelian, we can just transfer this and cancels. And so since the group is abelian or commutative, then our group is solvable. And so we can say that e to the yes, it's solvable. So maybe I will go to.
What do you mean by a group solvable? Because I don't think not everybody understands what it is.
So what I mean by a group is solvable, first of all, is some group G is solvable if we can dissect it or into a finite subchain of normal subgroups, such that for the groups we can always take the quotient of two consecutive subgroups, and this will be an abelian group.
Gi plus 1 modulo Gi. Oops.
Yeah.
Sorry, what does dissection mean?
What does this actually mean?
Dissect.
Dissect, I mean, we can create a finite subchain of, okay, imagine these being subsets, okay? And when I draw the triangle, I mean that it's a normal subgroup. And the normal subgroup means that you can always apply some action on this group, and such that when you apply the action to an element of the group, and then you apply the inverse, then this will give you n again. And for commutative groups, this is trivial. No, sorry.
I have a question. So, do you understand correctly that first we find the fundamental matrix and then make the decision about solvability? But as I understand, if we already have the fundamental matrix, then it's solved.
Yes. Yes. So the next example might help to solve this question, because in the next example, we don't have this.
Just a quick question. Whenever you add algebraic as an adjective to something, what does it mean? What's the difference between a group and an algebraic group?
So a linear algebraic group is a specific definition, which is just defined by a group that acts on a linear space, and this like an n times n matrix. So it's not like I'm just adding the word algebraic to give it some meaning, but rather the linear algebraic group is a specific type of group, and so I will show another type of.
Use the
Fresh.
bottom.
Perfect. And so, yes, this is kind of redundant, like circular, because we already know the solution. So, so I will go to an example where we don't have the solution. Okay. So, like the differential equation I talked at the start, we convert it to or like a system, and so this is now our partial y equals a plus y, right? And we want to find the fundamental matrix solution, and so we assume that we can't do this. So we assume that the functions that will do this are non-elementary. And so first I compute the Wronskian, and this is wrong. This should be a. I believe it should be. No, it's said. Okay, sorry. And so we can compute their matrices like or determinant, and we determine that it's just not equal to.
It should not be the determinant of A.
It should be the determinant of J.
Yeah, sorry. And then
So it's non-zero for C not equal to 0.
yes, but this expression I got it from A. So But okay, assuming that we get when we do get that this is not equal to 0, then we can conclude that they're linearly independent, and so this forms a fundamental matrix solution. And once we have this, we can now study the action of our group on the fundamental matrix solution. And so this is a linear algebraic group of 2 because we are in a second order system. And when we see that the determinant of these matrices is equal to 1, and then we can conclude that like there's not going to be no algebraic relations between our functions.
As in dependency.
Yes, they're basically like there's independence. That's the whole point we need. And so we get this result that I found in literature, that our group is equal to this group of the simple linear group of the complex numbers. And this simple linear group is a group that conveniently its name is named after it being a simple group.
I'm guessing the phi1 and phi2 form the basis for this group.
No, phi1 and phi2 are the non-elementary functions I assume to exist.
But the basis, the vectors of this matrix form the basis for the space.
Yes.
Okay.
Yes. Like these form a basis of the space.
Mm-hmm.
But psi1 and psi2 themselves, no.
Okay, amazing.
And so like this result is great result because now, as I said, like we can show that like the identity component is itself going to be equal to the group. And once we have this, well, this is great because we know that it's connected in the Zariski topology, and we know that the Zariski topology is non-Hausdorff. That's why we can assume this. And this group is known to be a simple group. And a simple group just means that the only normal subgroups that the group has are the identity element and itself. And so it's impossible to dissect or to convert it into a chain of subsequences. And from that, we can say that it's non-solvable. And so by Liouville's theorem, we have that we cannot solve this equation.
This is great. I was hoping you can wrap this up.
So by wrapping this up, so to wrap this up, yeah. I mean, what are the limitations of this? Like, it's horrible to do all of this for a differential equation. Like, no one wants to do this. And secondly, we're only dealing with nonlinear equations, which is going to be, well, just a very, very small subset of the equations that we're going to study. And we also assume that we're working over a field which is algebraically closed, which is not necessarily bad because it constrains us to having a system that necessarily is not gonna Well, I feel like most theory that uses field extensions and fields will assume this for facility, and because most systems are like that. And second, third of all, we don't use partial differential equations, and so there's no generalization or anything about this that we can apply necessarily. And so maybe this is like an interesting way of closing up and seeing how we can go over these types of systems. And we'll finally like the reason I talk about this is because maybe there's other formalisms for studying these types of systems. And well, this is a very specific case. It's like I'm looking at a very specific moment in a specific case, just because I have a motivation for a specific topic that Galois studied. And will I see like to what extent can I bring this theory to a point where it can be useful for something else? And I guess that's a motivation behind it, finding some way to connect algebra with geometry and with differential equations. And so yeah, like Tanaka representation is another way we can find the symmetries on the Galois group. But yeah, and yeah, that's it.
Thank you very much. That was very interesting. I hope everyone's okay if I actually ask the first question. So can you go back to the previous slide? So I was wondering if there were attempts to generalize this theory to partial differential equations. Are you aware of any?
So
into
the problem with this is we're kind of like basing this whole theory over the fact that our field is over like a field of polynomials of one variable. So in this case, like many of the definitions that are used in algebraic geometry, I believe you could be used because for most of the cases, I'm assuming that my affine space is for one variable. I'm assuming that I'm being very restrictive, mostly because I am not I don't know about these topics as much. It's more of a motivation for me to like understand how deep I can find this interest, but I'm not sure.
Mm-hmm. Okay, and then let me ask. What's your sample? Ask a question.
At the beginning, you said that you consider the coefficients to be polynomials. But in this unsolvable example, they are not polynomials. This is the reason they're unsolvable.
I don't assume it's polynomials. I assume it's polynomials for a specific example, but the only condition I need on the coefficients is that it's a field or a ring of functions. So I can even define it as some f of x, such that I can create some function of. So this could be rational functions. This could be rational
functions.
Yeah, and yes, I think the most important result for me, or like the most interesting, is how I can show that the Galois group is a subset of the linear algebraic group, because the structure of the linear algebraic group is studied in algebraic geometry very precisely and very thoroughly. And so once I can relate this differential equation to an algebraic group and use its properties, and I don't have to dig into what this really means, as long as I can bridge the gaps.
Also, small question: when you compute this W of x, where does this c come from?
Here,
this coefficient c.
Yeah. This is I think this is definitely a mistake I did, because when I computed the
it should be right, but where does it come from?
Like which field, like which
this is an arbitrary constant or what?
Yes, this is an arbitrary constant.
Yes, so where does it come from?
Like c, which is equal to all f elements of f, such this is where it comes from.
But why do we have here? It's arbitrary.
How do we
how do we get it?
Is this?
Mm-hmm.
So there are, I'm guessing there are these constants which are invariant with respect to the derivation.
Yes, but no, the problem is that we have no explicit expression for this, right?
No, we do not have an expression.
So,
yeah, okay. Okay, I see. Okay.
Yeah, go for it.
What should we classify as a solution to differential equation? Do we trivial examples or trivial solutions count? Like zero? Zero is a solution to this differential equation.
So
Okay.
zero is an element of the field. So it is like, as I said, it's not like I have a trivial solution or a specific solution. I'm more focused on finding the space of solutions. And of course, if you have a linear space, then you have a zero element, right? And if you have a zero element, then that's a solution.
So is this?
And also you can go through the, you can also go through the other perspective of the Zariski topology, and you can look at the, you can look at, I don't know, a specific point and look at all the functions that are neutralized by this point, or you can look at functions and find a specific subset of an affine space that neutralizes it. And in both cases, you can find zero to be further, like there to exist like an ideal for zero, or further to exist an affine variety for the for zero. Yes.
If zero is a solution, is it solvable? Is the differential equation solvable?
What counting as solvable is to actually solve for the basis of this.
Can you express zero as a? So let's go to the example. Like you're saying here, I can just express a 0, 0, 0, and it gives 0.
Sure.
I guess it's a trivial solution, yes, but
that's not the point.
This is not the point, but
finding the non-trivial solutions.
yeah, but yeah, it's a.
I can answer for that is that our solution lies in some linear space of the basis that comes after the Wronskian, right? And now, well, if it is a linear space, then zero is always present.
Yes.
And when zero is always present, that means zero is always a solution.
Yes.
Yeah. If the right-hand side was equal to 1, though, that would not be true.
Yeah, but that's like inhomogeneous.
Yeah, this is okay. Yeah.
So, like in example, you could say that since, like in your original field K, 0 is an element of this, and there is no restriction and at no point on the definition of the differential field that says that a solution doesn't exist there, but rather that if we want to find all solutions, that's when we construct our fundamental matrix solution.
Or at least some subspace of solutions. At least some subspace of solutions.
Yes, and like one of my no, what do you mean? What do you mean?
Like at least one solution. For example, a differential equation might have
many bases.
Two bases, right? Maybe one basis that can define a solution line instead of a solution plane.
So like the whole point of the Galois group is we're doing transformations of this matrix, and we are each time getting a new basis, right?
New basis that generates the same space.
Yes.
Okay.
Yes, because our differential automorphisms are coming from the field of constants, and when you think of it, you're basically taking some affine variety, and you're applying it to another variety, and it just gives another variety. I don't know how to like say it, but yes, and I think here in one of the slides I skipped almost. Like yes, when you're at like can't see here, but this is like y is g a subset of g ln c, and yes, it's like the solutions act like the operation acts linearly on the solutions of the vector space, and the relations themselves, they they define polynomial equations because, like, well, oh, how does M sigma even look like, right? Like M sigma is just gonna look like, well, this is gonna be a matrix of numbers. Like this is actually gonna be like some, I don't know, matrix such that preserves the linear system, and yeah, that's why it forms a basis.
Very good. Do we have more questions for the speaker?
I have some remarks actually. So the reason that it's called Wronskian is if you go back, more, yeah, here. So the matrix that you see, that is jet of x, is called a Wronskian matrix, and we are taking the determinant of that matrix, which is named Wronskian. The second remark that I want to make is SL2R, SL2C in this case is simple linear group, and I want to formally define this because we just established that it is simple, but the formal definition is it's a subspace of GL2C, which is general linear group, such that the matrix that we have has determinant 1.
Yeah.
And since our determinant of M sigma is 1, it falls under SL2C.
Yeah, this is the main property, right?
Yeah.
So this is what gives us this.
So any matrix that that has determinant 1 falls under SL2C.
Yeah. Okay. Thank you.
That's the definition. If this is it, then let's thank a speaker once again.